This intro is kind of designed to go either right in front of where we'd start talking about hypothesis testing or kind of along with it. It is originally a thing I put together for 270, as you can kind of tell right here, but we're doing the same stuff in this part. So for a single mean or a single proportion, what we're going to do is just like what we do in 270. So I thought this thing might be nice to have if you wanted kind of an extra resource. And really what this PowerPoint is supposed to be for is it's more about the logical underpinning of hypothesis testing rather than the mechanical parts. So we have to kind of go back and do some logic here. So with the truth table, where some people are comfortable with this and some people kind of haven't really seen this a whole lot or haven't seen it in a really long time, but what we do have to kind of go through here in order for the logical underpinning to make more sense would be where the implication here fails. So P and Q are just some statements. They can be whatever you want, and I kind of made up some down here that I think would fit with what we're trying to talk about. So if P is the statement that the fire alarm rings and Q is a statement that we go outside, then there are two possibilities for each of those, right? Each one could be either true or false, right? Either the fire alarm rings or it doesn't. Either we go outside or we don't. And so that means that there are four total possibilities up here, where we have true with true, true with false, false with true, and false with false. And then this third column with the arrow could be read out loud as the word implies, or some people phrase that as if P then Q rather than P implies Q. But it's a conditional statement. So if this thing happens, then this other thing happens. So the thing that's going to be the interesting outcome over here is the one that's false, because three of them are going to work and one of them doesn't. And the one that doesn't is the second one. So the first one is fine. If the fire alarm rings and we go outside, well, that's what you're supposed to do. That's how that's supposed to work. And then the one on the very bottom, if the fire alarm doesn't ring and we don't go outside, well, that's what happens the overwhelming majority of the time during class, right? We don't leave until the end of the class period, right? That's usually the way that it works. Then the two in the middle, so the third one, the second one up from the bottom, the false then true. So the fire alarm doesn't ring and we go outside. So maybe there was some other reason to go outside. Maybe sprinklers went off or something and it made sense to go outside, right? That's a possibility. The one that would be the bad outcome would be if the fire alarm rings and we don't go outside. So the fire alarm is going off and we're not reacting to it. That's the one that's the bad situation, right? So that's the one where the conditional statement, the P implies Q or the if P then Q, ends up being false. So that leads to this thing down here, this modus tollens thing, which you may have seen that phrase like in a geometry class. If you had a geometry class in high school and you had the proofs, that's probably going to be in there. So the idea there is if P implies Q is true, but Q is false, that forces P to be false. Because the other scenario where if P implies Q is true, Q is false, and P is true leads to a contradiction. And then you get P implies Q being both true and false. So thus, this would have to be true here, this statement. So if P implies Q is true and Q is false, then that means that P also has to be false. That right there is a lot of how the hypothesis test works in a general sense. It's this logical piece with a lot of statistics stuff kind of sitting on top. Another way to look at this idea is with something called the Wason selection task. And the way that that works is that you have four cards, which we'll see them, they're on the next slide. But you have four cards where two of them are face up and two of them are face down. And the sides that don't have numbers, on the other side, it's just a color. So the whole thing is red or the whole thing is blue or the whole thing is green, that kind of thing. And then we have to figure out which cards you have to turn over in order to test this proposition. So notice it's an if-then statement. So it's a conditional statement. If a card has an even number on one face, then the opposite face is red. Here are the four cards. So two of them have the number side sticking up, where one of them is an even number, one of them is an odd number, and then we have two with the other side facing up where they're different colors. And one of them's red and the other one isn't. The way that this is originally set up is that the other side is brown. I should have probably adjusted that to make it stick out more, made the other one blue or something, but we can make it work with the brown. Here's everything together. We have the conditional statement up top, the if a card shows an even number on one face, then its opposite face is red. And then we've got our 4 cards, and the 2 that you have to turn over. One is one of the ones that has a number facing up, and the other one is going to be one of the ones with the color facing up. The one with the number facing up, most people see that right away. That the one that you'd have to check is the 8. Because if you turn over the 8 and the other side's not red, that's a problem, right? Then that messes up that statement up toward the top of the screen. So if you turn over the 8 and it's blue, that's a problem. You turn over the 8 and it's green, that's a problem. But you turn over the 8 and it's red, you go, oh, we're okay. The 3, it doesn't make a difference what's on the other side, because that statement doesn't say anything about odd numbers. So you could have anything. If you turn over the 3 and it's red, that's fine. If you turn over the 3 and it's blue, that's fine. Or if it's green, that's fine. So what happens when you turn over the 3 doesn't matter, because the statement doesn't say anything about, if it's true that you have an odd number, then this is what happens. There's nothing like that. It's just for an even number, so you just need the 8. The colors are a little harder. So I think the natural inclination is to think, well, it mentions being red in that statement up there, right? Then its opposite face is red. It mentions redness. But the one that you have to turn over is actually the brown. So the reason for that is if you turn over the red and you have an even number, that's great, right? Those are the 2 statements that are referenced in that if-then statement up above. But if you turn over the red and it's an odd number, so if you turn over the red and there's a 5, that's okay, right? Because that statement didn't say anything about odd numbers, so if you have an odd number with a red, that doesn't mess anything up. The brown can cause a problem, because if you turn over the brown and you have an even number, like if you turn over the brown and there's a 4, that's trouble. Because then you have even number on one side, other side's not red. So then it messes up this conditional, because then you have the if part, you have the even number on one side, but you don't have the then part, because you don't have the red opposite side. So it's actually the brown that you have to turn over as far as the ones with the colors are concerned. This slide is kind of a summary of why you have to turn over which cards. So and especially for the ones that have the colors facing up. So if the implication is true and Q is true, meaning, so Q being true, I guess with the cards would be that you have the red color side, then P can be either true or false, meaning it's okay if you have an even number, it's okay if you have an odd number. And so we don't have to turn the red card over because we're safe with that one no matter what. But if P implies Q is true and then Q is false, this is actually the modus tollens thing again, where that forces P to be false. So this is the brown card, where if you turn over the brown card and you have an even number, that's a problem, right? That's going to mess up the conditional. So that's like if you had a 4 or 6 or something, that's going to cause a problem. But if you turn over the brown card and P is false, meaning that the number on the other side is odd, then we're okay, right? Odd number can have a different color on the other side, and that doesn't mess anything up. Now we get into some of the hypothesis test stuff. So this null hypothesis here, it's always a statement about the parameter. So that's why there's a mu. So mu equals 25, right? Mu would be a population mean. So if mu is 25, then you wouldn't necessarily expect x bar, the sample mean, to be exactly 25, but you probably expect it to be around there. You expect it to be close. So then if you look at these 2 scenarios down here, if x bar is 24 or if x bar is 47, if it was a 24, you'd say, okay, well, that's near 25. That's not weird, right? Sampling variability, that's going to happen. But if x bar is 47, you go, oh, that looks weird, right? If mu is really 25, that x bar looks really strange. It looks really big. So maybe there something is going wrong. So here's that idea. If mu is 25, you expect x bar to be around there someplace. You expect it to be close to 25. So in the situation where x bar is 24, that is close to 25. So what kind of conclusion could we make? Well, as it turns out, we can't say anything very strong. You couldn't conclude that mu is different than 25 because x bar, the 24, is pretty close to 25. So it doesn't seem like you could throw out that idea, but you also can't conclude that mu is that specific number. Just to play devil's advocate, what if mu was 23? Right? Then getting a 24 for the sample mean wouldn't be weird either, or if mu was 22 and a half or something. So you end up with a conclusion that feels like you're kind of sitting on the fence here, right? Where you go, well, we can't throw out the idea that mu is 25, but we also can't say it's that specific number. Mu might be around there, but it might be some other value, right? It might be a 22 instead, and we're getting a 24, and that's still close to 22. So that's also a possibility. And so really all we can say is we can't throw out the idea that mu might be 25. However, if you have a sample mean that is really different, so how 47, I think we can agree, not that close to 25, there you can say, okay, well, we have our conditional statement up here. If mu is 25, x bar should be close to it, but the second part of it, the then part, is clearly false. 47 is a lot bigger than 25. To say it's close to it, that doesn't really seem like that's where that is, right? It seems like 47 is much bigger. So then this goes right back to the truth table stuff. So here, the if mu equals 25, then x bar should be close to 25. That's the P implies Q. And we're saying, what if Q is false? So x bar being 47, it looks like that's the idea that being close to 25, that's false. So then you'd say, well then, the P, the if part up here, that would also have to be false. So it looks like mu is not equal to 25. So it's that modus tollens idea again. And this is kind of what I mean, where the statistics stuff just kind of sits on top of that logical idea that's there. And notice here you get a nice strong conclusion. And this can throw people off, where if you go one way, you kind of end up with a conclusion that's, oh, well, it might be this, it might be that. And the other way you go, okay, looks like this is what's happening. You get a nice firm statement like we're getting right here. So the two possible conclusions you get, they aren't really, right, they're not equivalent in terms of how forceful they are. One of them you can make a nice strong statement, the other one you can't. And that's a thing where if you haven't done this before, it does take a little bit of time to get used to that. I also put another one in here where usually the null hypotheses aren't written like this anymore. Usually they're just written as mu equals some number rather than with the non-strict inequality there. But I think for this example, it'll make sense to kind of play along with it. So if mu is greater than or equal to 90, what would we expect for x bar? Well, either that was around 90 or bigger, right? That would make sense. So that is the thing that we can say, that we'd expect x bar to be close to 90 if mu was exactly that number, or greater than 90, right? If mu is really 100, and you go, okay, well then you expect x bar to be around there someplace, so probably bigger than 90. So then what can we conclude if x bar is 93 or if x bar is 70? If x bar is 93, what we end up with is we just can't throw out the idea that's in the null hypothesis. But we also can't say that's definitely what's happening, because the 93 is not that much bigger than 90. So to play devil's advocate, what if mu was 89? Then getting an x bar of 93 wouldn't be that weird, but 89 is less than 90. So that would be a scenario where the null hypothesis isn't actually correct, but we're still getting a value of 93 out of the sample. So again, this is where we end up with kind of that weaker conclusion. About all we can say is, well, this is inconclusive, because that does fit, that 93 does fit with the idea of mu being greater than or equal to 90, but it's so close to that boundary, it's so close to 90, that it's also possible that mu could be a little bit smaller. So really all we can say here is we couldn't throw the null hypothesis out. However, if you end up with an x bar that's a lot smaller, so like if x bar is 70, that's a lot smaller than 90, and that's where you can say, okay, it looks like the idea that mu is greater than or equal to 90 is probably wrong. So here you get the nice strong statement. You can say, with an X bar like that, it looks like that hypothesis that we started off with, that null hypothesis of mu being greater than or equal to 90, it looks like that's wrong, and it looks like if X bar is that low, that mu is probably less than 90.